I am.
Yeah, for statepods.
Yeah.
I'm gonna talk about loans on Petri nets and all the horrible things of real life.
That can happen.
That can happen.
Yeah. Okay, so how many of you know what a Petri net is? Cool. Okay, I will recap it anyway. So a Petri net is basically a tool that has been invented to describe chemical reactions, but then it turns out that it's quite useful in computer science to represent processes and flows of resources. And the idea is that a Petri net is something that has places that you just represent as circles, and transitions that are usually represented as bars. And a place can have a given number of tokens in it that is represented as black dots, basically. Transitions are connected to places using arrows that can go inbound in the transition or outbound. And the way this has to be read is that this is a process that needs a number of tokens from each place specified by these numbers to fire. Usually when the number is 1, we don't write it because it's redundant. So in a situation like this, what happens is that this transition can fire. That means that this process can consume some of these resources, and then what you get is something like this, in this case. So this thing, two tokens from here, 1 token from here, and a token here. And with this thing you can represent quite a lot of concurrent computations and stuff like that. Now this is the most basic model of Petri net, but then this has been generalized in any possible way imaginable, and I mean, there are some properties of Petri nets that get preserved and some that get not, but the idea is that you want to represent a process as a Petri net, and then you want to study properties of this process, seeing if starting from a given marking or state of the Petri net, so a given displacement of tokens, you can reach another marking. And in this way you can basically do some kind of software analysis, some kind of analysis of your process. There is a paper by, Vladimiro Sassone that categorified the notion of Petri net. It's not the first one. There are other papers that did that. Sassone, Montanari, and other people worked on this thing quite a lot in the 90s. But the idea is that somehow you want to create a category that describes how the computations of Petri nets happen. And basically the result that they found is that the category of Petri nets and their simulation, the category of Petri nets and their simulations that I will define in a bit is equivalent to a category of symmetric categories. By the way, I got something wrong here now. Yeah. I don't know. Sorry. So yeah, you have symmetric model categories. And the way it works is basically following this receipt here. So places become generating objects of your category, so you can just mark them like this. And a marking just becomes an object in your category. So for instance, in this case, we could say that tensor C represents having 2 tokens in A, 1 token in B, and 1 token in C. Now, transition T, morally, that's where things become complicated, but morally becomes a process, a morphism, that in this case is taking 2 tokens from A and 1 token from B, and gives you a token C. And now you can represent how these various transitions in a more complicated net that can have many fire together, basically obtaining circuit diagrams. your category. So that's the general recipe they followed. Now, the reason why things become complicated is because your monoidal product here is not symmetric, while clearly the Petronet doesn't distinguish if you geometrically turn these places upside down. So it turns out that if you impose commutativity on your monoidal product, then it doesn't work anymore. The way it doesn't work is because in the end you want that morphisms between these Petronets will correspond to functors between these categories. And it turns out that if you require the product to be symmetric, then there are some morphisms between Petronets that cannot be represented by functors.
So this is just a purely categorical requirement then?
It's not really a purely categorical requirement. The point is that morphisms between nets, that we'll define in a second, represent simulations between nets. So if the category represents how computation in a Petronet is carried on, and a Petronet can simulate another Petronet, then you would expect that you can functorially map these computations into these computations.
But if you take a single Petronet, you can do.
Yeah, you can, and that's what the first paper they brought in. What they did in the first paper, they had this condition. I think it was a paper by Montanari, Melgratti, and other people. But then, yeah, they realized, oh, actually, we can't really represent well the idea that simulations of nets become functors. So they dropped this requirement and got something a bit more complicated. But I'll get to that.
I have another question that's arises from a physical perspective. So that the number of, let's say, of tokens that you need to fire this thing is fixed, or is
in the standard model of Petronets is fixed. But there are any kind of flavors for that. There are even Petronets where you have logical conditions here. They're called guards, and so they basically tell you that you can fire.
Maybe we can talk about that, because in resource theory this has very interesting parallel with that. But in general, one doesn't fix the number of resources you need to trigger.
So the way this is useful for us, for this startup called Statebox that we are starting up, is that I can represent basically the topology of my software using these things. So I don't know, for me, these could represent the idea of doing a quick sort. So this can have type list, this can have type list, and this can be quick sort. But then the point is that when I design my piece of software, I can abstract from this information, and I just assign the Petronet. And then what I do is that I can basically functorially map these processes in my category of computation of Petronets into some piece of Haskell or other functional programming language, actually giving meaning to what I'm doing. So that's one of the reasons why we were looking at this thing. So the first thing I'll do now is I'll formalize what a Petronet is mathematically. So the first notion that we need is the one of multiset. And a multiset on P is just a set composed with elements of P. P is a set that can have repetition. And we represent it just as a function from P to the natural numbers. And if P is like AB, then in here you can also represent, this thing can also represent stuff like AA or ABB and whatever. You're just saying A gets mapped into 2, B gets mapped into 0, A gets mapped into 1, B gets mapped into 2, and whatever.
And P is assumed to be finite?
Huh?
Is P assumed to be finite?
Yes. Not really. What you assume for this thing is that there is only a finite number of elements in here that get mapped to something different from 0. So I put some notation here. Basically, I will denote with M, P, M, the set of multisets on P. And it turns out that this thing is a free commutative monoid generated by P. Yeah. Okay, so a Petronet can just be represented as something like this, where P is a set of places, T is the set of transitions, and these things are called input and output functions, and they are basically telling me how transitions are connected to places, and they are basically functions like this. So to each transition, I'm associating a set of a multiset on the set of places. And you can see that if I have a situation like this, I could say that this corresponds to the multiset that assigns 2 to A, B to 1, and C to 0. And this is for the inputs, for the ones that go in this direction, and this one is for the outputs that go in the other direction. Yeah.
That is meant to be the free abelian group generated by S?
Which one? This one?
Yes.
No.
Just the free group.
Yeah. I'll get to that in a second.
So you said P is allowed to be infinite. Is T also allowed to be infinite? You don't allow, because if it were, then wouldn't you want to require that function to be finitely supported as well?
I think it's required to be finite. I really don't remember, but yeah, it's in the end it's even finite or is infinite with finite support.
The functions.
Yeah.
Okay.
But anyway, so I mean.
Wait, what does it mean to have finite support in that?
No, I think T is finite, honestly. But
Okay.
You mean the image, all the elements in the image are finite?
yeah, I mean.
Yeah, all but finitely many elements of T would be mapped to.
No, but this is sorry.
No,
this
right.
is the set of finite multisets on P.
Yes, but even so, that doesn't. If T is infinite, that doesn't stop you from having a non-finitely supported function into the finitely supported multiset. So
Oh, I see.
Yeah, but you can have infinite transitions. But the point is that each transition has a finite number of places going in and a finite number of places going out.
Right, well that's not, the fact that M has a finite, the definition of your MN thing includes a finite support condition isn't enough to ensure that there's only finitely many things going in and out of a transition.
Yes, it is.
It's not, because you could have
it is. To each transition I'm assigning a finite
I'm talking about
multiset.
it.
Yeah, so places can have infinitely many transitions.
Okay, anyway.
Yeah, forget what I said.
Then we represent a state on the Petri net, so a number of tokens in each place, just as a multiset on the places. So states are just multisets, finite multisets in M. Okay, so this is what people did. This is quite standard. And what we did at some point is we asked what happens if you can allow negative tokens in your Petri net. So what happens if your places can have these things, but also these sort of -1 tokens going around. And then the first thing you do is you generalize this definition in a pretty obvious way. So you can do it. The first thing you can do it is you take this thing to be exactly the same, but you also allow for states. You are allowed for states to be integral multisets, and this means that now a multiset doesn't go anymore from P to natural numbers, but it will go from P to the integer numbers.
Okay, so those things cancel out.
Yeah, this can cancel out. And the second generalization that you can do is you allow also these two things to be like this. And this means that now a transition can also consume like -1 tokens or -n tokens from some place. Now, the first thing we want to do is to define a category between Dallas Petriness as objects and simulations. Sorry, yes?
Is there any difference between consuming -1 tokens and outputting a token?
Sorry?
Is there any difference between consuming -1 tokens and outputting 1 token?
We'll get to that in a second. So what turns out is that your category computations will be compa closed, and basically what you're asking equals to taking the transpose of a morphism in the compa closed category. So you have all this weird stuff that a pattern that carries 1 into 1 is like a transition that goes from 1 to 1 corresponds to a transition that goes backwards from -1, -1. I'll get to that in a second, yeah.
Well, this entire construction as of now seems to only hinge on the fact that that's, let's say, some monoid, commutative monoid perhaps?
Yeah.
Does it need to be a semiring, or is it enough to be a commutative monoid?
At the moment we just looked at commutative monoids, but you also need some form of freeness to do it. I'll go to that in a second. You can, I'm sure you can generalize this to monoids or even rings and semi-rings, but I really didn't work on that.
Do you ever use the multiplication in any case? You ever use multiplication between values in any way that is interesting?
No.
Or only use additions?
Yeah, at the
So
moment.
you essentially just need monoids. Okay.
Yeah, no, for this we just need a monoid, but it could be actually nice to have a more complicated algebraic structure that can represent some non-trivial interaction between tokens in a place. But I didn't work on that at the moment. But anyway, morphisms of nets. So, as I said, the set of multisets is a free commutative monoids, and the set of integral multisets, so function to z, is unsurprising the free abelian group. So, how you define?
So it is the free abelian group. It's not just it's not the free group.
This is the free abelian group, not this.
Okay.
The integral multisets is a there are free abelian groups. Now, morphisms of net that goes from say PT and to TM, M. It's just a couple of functions, fg, where f goes from Tn to Tm, so I'm mapping transitions of this net into transitions of this net, and g is monoid homomorphism that goes from MPN and to MPN. And these two things have to interact in this way. I have this, then I can go here using stuff. I have G here. So this is the classical definition of morphism between Petrinets. And basically what it's telling you is that this thing has to map transitions into transitions, but then this thing has to take care of the fact that the preconditions and postconditions for a transition have to be preserved in a nice way. So you have this diagram and another one that is exactly equal to this, but with the output things here. And obviously you can generalize this to our integral case, just requiring these things to be like this in the case of integral Petrinets, so in this case here. But notice that if we just require the states to be integral multisets, so tokens in places can be negative, but transitions cannot consume negative tokens, then the old definition is still okay. And so you get this thing that may be surprising in the beginning, but you have three categories of Petrinets that I've written here. Classic Petrinets, everything is a natural multiset with morphisms between them. Category of Petrinets, everything is natural but the states. And category of integral nets, where I'm changing this thing too. And these two categories are equivalent. These two categories are actually equal. These are the same thing. Because the concept of marking is not captured by the definition of net and the definition of morphism. So these two things are actually not even equivalent. They are actually equal.
Okay, wait. But how can they be equal? They have different generators?
No, they are not, because the only difference between these two, the object of this thing are this, the objects of this thing are this. The only difference is this. But this thing is not captured by the notion of morphism. In both cases, morphisms are a couple of functions.
But isn't that captured by the objects that you allow?
No, the objects are nets. And a net, as an object, doesn't have any definition of marking on it. This is actually a very fucked up thing in Petri net theories, that you never really understand if the marking is part of the definition of a net or not. But it's taken not to be. What you really do is, you define a net like this, then you put a marking on the net, and then you give firing conditions for these tokens to go around.
So it's not embedded in the definition of the Petri net through the mappings on from transformations to what I may be tempted to describe as the state space.
No, because it's not.
That third line there.
Because it's not the state space.
Okay, but in the case of the natural numbers net, wouldn't that be calligraphic M subscript P superscript math bold N? Yeah, so I mean, there's perhaps where the distinction would be smuggled in, which is part of why Stefano and I might be a bit confused.
In the case of what I call semi-integer nets here, the definition of net is the same, because you're just telling what places are, what transitions are, and how input and output work. The state gets put on top of it, and it's external to the definition of net.
It's how it works, but that how it works
does not capture what you're actually describing, because you have no way of talking about the state, so you're not talking. So that's not actually directly. I mean, that's a category, sure, but it only captures the transformations, not the running. So you can't run the Petri net.
Exactly. And that's exactly the problem. In these categories, I'm just defining the Petri net as geometric entities, but there is no way to capture how they run, because I'm talking about tokens here. Okay, so
anything with an action of n on it would be a suitable.
Yeah.
So that could be
a suitable state. Yes.
That would even be, it's a monoid, right?
Yeah.
So that could even be like a cyclic group or something.
Yeah. Yeah, you can generalize this thing wildly with all kind of crazy stuff. So, okay, so now we want to build categories and that correspond to these things. This category, in the case of standard patterns, is being built by Sassone, and what we did was building these other two for the semi-integer and integer case. So, okay, the way it works is like this. Remember the main recipe that is this: places generating objects, transitions generating morphisms, and blah blah blah. I'll get to that in a second. So what I did is this. You take a set, and you generate the free, strict, compact, closed category on it, modulo these axioms. The objects of this thing can be identified with strings that look like this, where these ones can be 1, 0, or -1. So you're just saying that an object in this free strict compact closed category is just a monodal product of stuff or adjoint of stuff. You can represent the adjoint as a -1, and you have this string representation. And so you see that the set of objects of this compact closed category is exactly this: is the free group generated by S.
You said it could be 1, 0 or -1.
1, 0
or to be 0.
Huh?
Why would you want it to be 0?
Because in that case, it's the monodal unit. When it's 0, it
But
means
it's supposed to be strict, so the uniters are supposed to be identity, right?
yes, yeah, they disappear basically. Yeah.
Also,
I don't understand. If you allow the superscript to be 0, then surely that implies the uniters will not be strict. Well, the uniters will not be identity.
But if you identify this with a free group and one of these is 0, then this is equal to this.
So it's equivalence classes of those things.
Yeah, it's exactly like the set of words on a free group, basically.
But that's not really a free group, right? It's not, because x to the 1 and x to the minus 1 don't give you 0. Because you didn't write the second condition for the cup to cancel out the cap, so that's not true. Now, that says that the cup is an isometry, but doesn't say that it's an isomorphism. Doesn't matter. What is that?
Strict.
Doesn't matter.
In the sense of telling Laplace that it does.
No, wait a second.
Just a second. No, I have a footnote to clarify this thing.
Definitely not a free group. It's the free mono generated by 2 copies of this set, not the free group. 30 seconds.
I have it.
Also, you need more than strict technically.
You know, I'm requiring that A tensor B adjoint is equal to B adjoint tensor A adjoint, I adjoint is equal to I, and A adjoint is equal to A.
Sorry. Yeah, okay, that's not enough to make it the free group. It's definitely not. You missed one equation for the cup and cap, and you need to do skeletal for it to be a group. So that's clearly.
You don't want a free group as well, right? So it's good.
No, but he's just said it's a free group. That's why I'm just asking.
I'm saying that this is a set of strings that look like this.
No, it's not.
It is.
No.
So you just have a unit law.
There is a
That's
quotient
it.
on that set of strings, so it's not true. That's not what you want. You don't want the free group. You want the free mono generated by 2 copies of the set.
Yeah, I have to dig into the details here, but I check this stuff out. I mean, at the moment, keep going.
In order to get the free group, you need to have an isomorphism between A star tensor A and the identity. And you need to strictify.
A star tensor
So you
A.
need the opposite of that cup equation. No.
No, the
Which one?
you get cap, then cup equals identity. That's like,
Oh, yeah, okay. Plus.
Strictify. But that's not important. Who cares about that?
Yeah, anyway, let me keep going because I think I won't be able to finish anyway. So, so basically what you do is that now you have this category that I denote as GS, is this category here, and this represents my bookkeeping in the category computations. So basically the morphisms here are tensors and compositions of identity wires, this kind of thing, this kind of thing, this kind of thing, according to these equations.
Including red or not including red?
I think including red.
Oh, okay, that's
What they represent is...
wait, really? With the red one?
because with the red one it is actually the free group.
But I don't think you want it to.
No, he wants to cancel out +1 and -1 in these states, so you need that, right? Otherwise you can't.
Is that what you want to do?
I'm pretty sure that's how you described it.
No, you don't want an equality there.
What do you want? Well, you want an isomorphism.
No, I think you're just building the free
Mono.
strict compact
So-
categories, and I think you're right. The 0 shouldn't be there, but otherwise, definitely there shouldn't be
So no red equation.
the isomorphism.
Yeah, that shouldn't be there because you want to represent the idea that token can be created and can be destroyed and annihilate with each other as a process happening. You want to keep track of this thing.
Yeah.
Yeah, but do they represent the same state or not? I mean, they may be different state but isomorphic. That means that they're the same state. Up to
Yeah,
a process.
Let me tell you what this represents.
Yeah.
So this wire, type Y, represents a token in place A, basically.
Yeah.
This thing represents the idea that if I have a place, since now I have negative stuff, I can basically create negative tokens
Yeah.
in this place. These represent the opposite, I can always destroy them.
Yeah.
And this represents the idea that if I have a token in A and a token in B, and I represent it like this, I can always represent it as inverse because these are really maps.
But your equality is given by the picture with the dots, right? So that is your state. You want them to be different. You want the empty circle and the circle with the red and the blue dot to be different, but you want to know that there is a process going back and
Yes,
forth.
exactly.
Then you want the red equation as well.
Okay.
Because that's take one blue, one red dot, go to empty, and then go back to one blue and one red dot. That is an identity.
Is it though?
Yes, and that gives you the free group. That's what that is.
I'm not sure that you want that because no, actually you don't want that.
You don't want that.
No, because if you have a process like this that outputs a positive and negative token, you annihilate this. You are losing history here. You are recreating them, and you don't want to say that these two processes are concatenable. You don't
So your state is not defined by the picture. It's the history of the picture. The pictures don't define the
yes,
state.
exactly.
Oh, that's not what. Yeah, okay, so that's the opposite.
Yeah, no, you don't want.
You don't want that. So
Okay,
it's not a free group. Okay.
It's the monoid generated by S and S to the -1. Okay, cool. Now, the free monoid, sorry.
Yeah, of course.
Modulo stuff. Okay, so now what we do is we call an arrow in here basically structural. So, okay, now first of all, let me define what an integer Petri category is. An integer Petri category is a strict, compact, closed category such that the objects of C are basically in bijections with the objects of GS for some S. So you are saying that the set of objects of this category can be represented in this way. Yes. Okay? And now you can say, since this is a compact closed category, you can identify morphisms that are just compositions of swaps, caps, and identities. So basically all the possible bookkeeping that you can do with these wires. Okay? Now I can say that morphism tau is primitive if tau is not structural. That means that it's not a tensor of compositions of wires. It has to be something more. If tau is equal to A alpha after beta, then either alpha is structural, in this case is primitive, B primitive, or vice versa. I'll tell you why this is important in a second. And you have a similar condition of tensor. In this case, you say that this is the identity of the monadic unit and beta primitive, or vice versa. So the idea is that now you take a morphism tau in this category, and you want to say that somehow this morphism is primitive if I can decompose it as some wire swapping caps and caps on both sides, and something in the middle that is not further decomposable. Okay, now, why is this thing useful? This thing is useful because, since, as I said, places are somehow commutative, but morphisms, but objects are not, I can't really say that for each transition I have a process in my compact closed category. What I have to do is that for each transition, I want to get a process in my category for all possible swapping and addition of caps and caps on both sides of it. And this process will all be identified because they will be primitive and they will be the components of some natural transformations in my category, living in my category. So what we do now is, if I have...
Your free compact closed category is over two sets now? Is it over one set? Because you have a set of places and a set of transition?
At the moment, I'm still not defining that compact closed category.
Okay.
But the set of places will be the generating objects, and the set of transitions will be basically the generating morphisms.
Oh, so yeah, I'm talking about the morphisms.
Yeah. So, now what I can do is I can define an M, this one, and this M basically goes from this set of strings to integral multisets. And the way it works is M of a string on P, because this has to be a function from S to Z, just counts the occurrences of P in S minus the occurrences of P minus 1 in S. So you're just saying how many P's and minus P's there are and you sum up.
So is SZ of P is the free monoid on P plus P?
Is the monoid generated by S, the formal symbol S minus 1, that is all the stuff in S exponentiated by minus 1, and the unit.
So it's a free monoid generated by S plus S. That's the joint union S.
Oh, so S is a set, and SZ is the free monoid on S plus S?
Yes.
Yeah.
Okay.
So it should be N.
So, what you can do with this thing now is defining if C is a Petri category and the objects are generated by S, then I can define G C nu, where nu is an integral multiset, and the objects are defined to be the objects of C such that nu equals objects of C such that equals nu for each S. So the idea is that now I'm restricting all the objects of my category that are strings that get in the same multiset, basically. So for instance, this string and this string will give me the same multiset. And these are both objects of this if nu is the multiset that carries x in 2 and everything else in 0. So now what I can do is defining a transition in a Petri category as a natural transformation G C nu G C prime C C such that this is primitive. And this horrible condition is basically telling me that if this is a component of this natural transformation and I do some stuff like this, then this will basically be equal to another component of this natural transformation. Looks like this. A, B, C, D, A prime, B prime, C prime, D prime, A, C, B, D, A prime, C prime, B prime, B prime.
B prime, C prime. No, on the right, B.
Yeah, they switch.
Wait, no, what? How they can't be equal if they are different.
Oh yeah, sorry, yeah, different type. Yeah, absolutely. Yeah, no, you're right.
Yeah, okay, that makes sense. That makes sense.
Yeah, the idea is that these things can be absorbed by this thing, and what you get is another component of the same natural transformation. And then you, for these things, because these functors, this is projections, these are projections, and these are just injections. And basically what you're doing is, you're selecting a bookkeeping on the left, a bookkeeping on the right, and you say that all the processes that have this condition with respect to this bookkeeping define a natural transformation between these two. And this is important because now I'm basically finished with all this stuff. This is important because now you can define a category, and I won't go into details because I don't have time, called GX Petri, that has basically...
So wait, the natural transformation is between the functor that goes from G, E, B,
between this and this.
Okay, so it's an arrow. Okay, doesn't matter. Yeah. Yeah, okay. Alright.
Yeah, I mean, it's not, it's like...
Yeah, it's in the middle.
Yeah, it's horrible. Yeah, okay. Objects are Petri category, and morphisms are basically transition preserving functors that are strong monadal functors, such that every time I have some components of a tau, they go into the components of a theta that is a transition in the target category, modulo some equivalence relation that I don't have time to define now. But what you can get now is this. Given a net n, p, t, I can define a Petri category such that this is basically, let's call it n bar. This is the strict compact closed category, plus the arrows inferred by this with and again, the idea is that for each transition in T, I'm adding all these morphisms for all the possible strings that will be mapped to the input and output multiset. And then obviously I have also to say that if I have this, then I can have this. This is U. And if I have tensor, yes, if I have this, I have again to close it up, then I can have this, V prime, basically I'm generating a compact closed category where I include a morphism for every possible combination of this kind, and then I impose the axiom that I basically wrote before. So the one that tells you that wires can get it. And then what you get is that from this thing you can define these categories, X Petri n.
So what is that equation with lots of squiggly things? So does it say that Ys of the same type can be swapped sort of within view?
No, what I'm saying is that
because yeah, you would kind of,
if I have this, yeah, sure, something else. Okay, I can, yeah, I can do this. So I'm saying that each morphism tau that gets inferred from the transitions of the net is such that if I have this, there is another morphism tau prime that I can infer from the transition of the net that is equal to this. So the idea, this expresses the idea that all these morphisms that I'm getting in from each transition are in just because I have to keep track of this horrible bookkeeping, but they are basically morally equal. That's the idea of this condition.
But, sorry, so in this case tokens can be created and removed. I'm still trying to grasp what the semantics of this is.
Yeah, because in this case, basically what I'm saying is that I have a place with 0 things in.
No, but so your semantics are not actually the circles that you draw with dots in. Those do not define what your states are, because you want the entire bookkeeping. And you want to even keep track when you have two tokens of the same color. You want to keep track when you invert them within the same, right? Because the swap on A tensor A is not the identity on A tensor A.
Yeah.
So you keep track of that, but you don't want to keep track of the fact that if you have blue, red, blue, that is equal to blue.
Yeah, I mean, the way you keep track of it when you do the semantics is depending where you draw the cap. So like, if this is A, then you would represent this thing as A star. And now obviously if I want to represent that these two get erased or these two get erased, then I can decide if I want the cap here or I want the cap here. So you can select which one this thing annihilates with.
No, but I mean, if you start with a token, then you create two tokens, one positive, one. Start with a positive token, create two tokens, one positive, one negative, and then annihilate the other way around.
Yes, you can. You can.
But okay, yes. So that thing there is that's the identity.
Yeah.
That's not bookkeeping. You don't remember that.
No, you don't remember that.
Why that? Why don't you remember that? Why you don't remember that? But you
actually, that's exactly very useful. I'll tell you why in a second. But that's exactly why this thing is useful.
Okay.
So yeah, basically what we proved is that you have equivalencies of categories here. These categories are all full subcategories of these GX Petri with some restrictions on how these transitions in the category have to look like and what the morphisms do. Okay, so this is basically the maths, and the way it works and the way why it's useful is this. So imagine that you have a Petri net. You have something like this. Now these two transitions, imagine that this Petri net is running decentralized somewhere on the network, whatever, and you have a user U1 and a user U2, and they can basically, U1 can decide to fire this, and U2 can decide to fire this one. But they live in very different places. So what happens is that U1 fires, and so the situation of the net now is this. But then U1 has to broadcast the fact that the net has fired. But since broadcasting actually takes time in real time to happen, it could be that this other user submits fires too, basically. And now the net is in an overall illegal state. Because they both fired, but they can't. I mean, the model doesn't allow you to do that. What you can do now is you can represent this with a negative token. You can say, okay, actually now the net is in an overall illegal state. And the reason why this can be useful is...
But that doesn't require you to have a strict snake equation. You could just have the bookkeeping to create things.
Yeah, but give me a second. So now if I have this net, I have this net here with a token here, and I represent this token X, Y, Z, tau, mu, no? I have this. Then tau fires. Representing this. And now we are here. Okay. Now what I can do is this.
Is there a difference between open bars and colored-in bars?
No, it's just me being stupid.
Okay.
No difference whatsoever. So now I can create these two. This is Y.
There's a dot on the top. Okay.
Yeah. Alright. These fires. This is sets. I think I'll have to cancel some of this stuff. But now this fires too, putting this back. And this is mu here. But now I can annihilate these two tokens. And that's exactly why I wanted the snake equation.
Well, why do you want it? Okay.
Because the point is that now I can strengthen this wire, eliminate the negative tokens in the picture. And basically what I'm saying is that if this stuff happens, and here we had an illegal situation that then gets fixed, because in the end these two annihilate. So you have legal, legal, illegal, 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 legal. By strengthening the wire, I have a solution to automatically get something similar without the illegal states in the middle.
Okay, but sorry, this seems just to be related to the fact that you're capturing exactly the semantics of what those diagrams look like. But you're not in a lot of other cases. This only happens for the snake equation and the cup followed by the cat. But for example, it doesn't happen for the swap on two copies of the same token, which should happen. Because the picture where you have two dots and you pick the top one, and the picture where you have two dots and you pick the bottom one are identical from a pattern and semantics perspective, but not in your categorical semantics. Because the swap on an object is not the identity on the object.
I have to think about it for a bit, but yeah, probably you're right. But in that case, I feel this is easily fixable.
Oh yeah, absolutely.
I have to check.
I don't think it's a problem. I'm just asking whether there's a motivation explicitly, or you just didn't think of it.
Isn't it more about valid runs, though? It's more about valid runs of the thing. So he's adding a transition for each swap as well of the basic transition. So here this is telling you something else about entering what you call illegal states and then being able to go through non-illegal states to do that run.
Sure, but it doesn't behave as a multi-set if you have a non-trivial swap in bookkeeping terms. Because swapping two tokens in semantics of a Petronet means nothing.
No, of course. Yeah.
So that's while the distinction between positive and negative means something, because you're not dealing with a free group, you're dealing with the free mono generated by S plus S.
Yeah.
So the distinction there has a legality thing. Having two tokens of the same color and deciding to pick one or the other shouldn't mean anything. So the swap should be trivial.
But it's more about what you can do or not, I think.
But that's not. That's
actually, I'm not super. I don't super agree that the swap should be trivial. Because the point is that when you actually give meanings to these things, if you think about places as data types and tokens in a place as terms of that data type, picking one or the other is different.
Wait, okay, that's not, okay, we should probably talk about it in the separate instance, but that's not the standard semantics for the Petronets in general.
I agree, but the problem is exactly that we don't want the standard semantics.
No, but it's not even the extended semantics with its positive negative tokens, it's something more, and then one could just simply ask, why don't you just want to keep track of the snake equation as well then? Or why don't you want to keep track of the fact that you created two tokens and then deleted them? So there seems to be some deliberate choices.
Oh yeah, absolutely. But
so the
choices are driven by the implementation, obviously. But
exactly. So I'm curious to see
using this stuff.
Exactly. I imagine that there is. This is what I'm trying to understand. What drove certain choices and not other choices.
But the nice thing is that there was this paper I didn't know anything about negative and fractional data types by Sabri and other people. And basically, their idea is that they use negative data types exactly as types that are expecting an input coming from another computation. So what we'll try to do now is try to understand if this thing or an extended flavor of this thing can actually capture this idea and if we can implement this.
So you said you want to think of each place as being a data type, or you want the set of places to be a data type?
You can think about each place as being like a data type.
So in that case, why use multi-sets in the semantics? Because
Because you could have a process that takes, for instance, 2 lists in and spits a list out. And so you represent it as a transition with a 2 on it, saying I'm taking 2 terms of type list and I'm spitting out a term of type list.
But multi-set, I mean, that means the order doesn't matter.
Yeah, so you can't implement append in a useful way.
Yeah, but that's exactly why when you switch to the categorical point of view, you want actually to keep track about this kind of thing.
In which case you wouldn't be using multi-sets.
Yeah, that's not the same semantics.
Yeah. It's
So
not,
you change the semantics, it's not sets anymore.
yeah, it's quite tricky actually, but yeah.
What's called lists?
Huh?
The lists.
Lists. Lists.
Yeah. Instead of multi-sets, you
Sure.
just...
Lists.
Yeah.
To pick some obscure data to spell instead of.
Yeah, but anyway, the idea is that from the Petronet point of view, you really want to be as hurried as possible, actually, because you just want to abstract as much as you can. The way we are implementing this, for instance, is when you have a process, and this is what the user sees, and you have something like this. The user first clicks on the token, and what he gets is a list of what that token is. Yeah, there is something that pops in, says, okay, this token represents like this booking order with this date by this person, and then the user can decide which one of these 2 transitions has to fire to process this thing. But the point is that if I imagine that I am like booking trips or something like this, and I'm doing many bookings, I want to visualize that I have many tokens in a place that represents these trips are at this stage of the booking. And that's what I want to visualize my data. Only then I want to be able to click on one of them and get the details and telling to my server or whatever which one has to be processed by which kind of thing. So like cancel order, keep going pay, or these kind of things. So it's actually much easier to implement than to do it mathematically in some respect.
Wait.
But if like in the example you have,
Yeah.
the sort of the bottom user, he clicks on, like at some point there's this token, anti-token creation, he clicks on the token. This one doesn't have a history, right? This
what will happen, and this is why we are still trying to understand if this thing can be useful or not, is that when the user clicks, it sees the history because it didn't get the information from the other user that thing was processed. And then, when basically you get this, when you strengthen the wire, for instance,
all of a sudden he has a different token.
Things get scrambled. Like, he was thinking that he was processing this, while what he's processing is this after this and this happened. But there are some situations in which this may not be a problem. It really depends on the application. Clearly, if you think about the booking order example, this is really bad.
I mean, if you think of places where this is not a good.
But there are other examples, I think, especially when you try to use this stuff to design protocols or stuff like that, where this thing is not that bad. Or when you implement it, you can actually actuate something similar only in certain cases and not in others. It's a bit tricky. It's not that easy to understand why you can use it, but basically the way this thing was born for us was just out of curiosity, and now we are, sorry.
Oh, sorry. So if you have this the history that's implicit behind some of these tokens, and the history for some of these ones that are created from a token anti-token pair, essentially that creation event is its history, and then eventually the anti-token gets cancelled out. It seems like something which is a function which is a composition of transformations that's just awaiting the input. So is that simply the sort of semantics that you'd have behind that? This is sort of an abstract picture for it.
I get it. It makes sense now. Now it all makes sense. It makes sense why you don't want the swap to be trivial. It makes sense why you want the snake equation to be trivial. This makes sense.
Yeah, exactly. So
okay.
Yeah, I think probably to make sense of how this thing should work is exactly, think about this as you are trying to do something with a resource that doesn't exist anymore, or never existed for some reason. Yeah. So what I can do is I make a debt for you. I'm telling you, when a resource of this type will come in, I will actually satisfy your requirement and do this kind of stuff. Before then, sorry mate, you have to wait. So
you're doing as much paperwork as you can beforehand until finally you get the information that you can work with.
But even so if you do it from a functional perspective, then you might say that you have that's just packaged and you can't do anything to it, but you can start applying and simplifying above it, and then when it comes, you substitute it.
So the idea is that you want a machinery that somehow can do as much work as it can for you. But obviously, you can't take care of it. I mean, there will be situations of conflict where you actually want the user to choose. It's very similar to what Git does. If me and you are on Git and we edit different files and we push, Git just solves the conflict for you. If we both edit the same file, then that's a fuck up that Git can't solve on its own, and you will be prompted for a choice. And we are trying to represent something that is vaguely similar to this. Like in many situations, you will probably get something that is, again, this could be edit file 1, this could be edit file 2, and then it doesn't really matter when you strengthen if the order is crumbled. But there will be other situations in which you want something a bit more refined.
Thanks.
But this is basically the idea we were thinking about.
Makes a lot of sense.
And now we want to understand how this relates with all the literature there is around about negative data structures and whatever, on which I don't know anything at the moment. So I'll have to read quite a lot.
So who was it you said, these negative and fractional data structures?
There was a paper by some people. One was Sabri. I don't remember the other people. I can let you know.
How long ago are we talking? Like 90s or something?
Probably. I mean, a colleague of mine at Statebooks that does logic programming pointed this thing out to me, so he knows much more about this stuff. But anyway, now this paper we submitted it to QPL, me and Jelle Herold, that is the other co-author. It got accepted, and I think you will find it on the archive in a bit. Like, yeah. Can I publish something on the archive before QPL?
Yes, of course.
Okay, so I'll probably drop it on the archive today or tomorrow. Yeah. So yeah, I think that's it.
All right, thank you very much.
Any other question or?
How do we get out without being videoed?
Well, we can
yeah. Thanks.